Hi, I'm Rachel Gehlhar, and today I will present our work on separable control Lyapunov functions with application to prostheses, where we construct a CLF for a subsystem, namely the prosthesis, and a CLF for the rest of the system, the human, and obtain a CLF for the whole system that guarantees stability even in the presence of impacts and zero dynamics. Here's a video of me walking with the powered prosthesis Ampro 3 at Caltech. We studied powered prostheses because passive prostheses increase metabolic costs and hip power, whereas powered prostheses provide net power and enable healthier gait for the user. Currently, prosthesis controllers are model independent, lacking formal guarantees of stability. Res CLFs are a special class of CLF controllers that provide formal stability guarantees for bipedal robotics, but cannot be applied to the prosthesis due to unknown human dynamics. In this work, we develop a class of subsystem controllers using local information that guarantee stability for the full order hybrid system with zero dynamics. To give a brief overview of what I'll present today, I will explain what hybrid zero dynamics are and why we study these types of systems when studying walking. I will then explain what the special class of Res CLF controllers are that are constructed specifically to stabilize systems with hybrid zero dynamics. Then I will present the framework of separable systems, which allows us to consider only a portion of the system that does not rely on the control input of the rest of the system, such that we can construct controllers based only on local information of the subsystem. With these constructions, I will present the main idea of Theorem 1, where we construct a Res CLF for the human part of the system and a Res CLF for the subsystem, the prosthesis, to obtain a Res CLF for the whole system that guarantees stability for the hybrid zero dynamics. I will also present the main idea of Theorem 2, where I show how we construct CLFs based on the outputs that we linearize, and that with this construction, we can meet the conditions for individual components of a block diagonal structure to obtain a CLF that is stable for the whole system. With these constructions and Theorem 1, we result with a controller for the prosthesis subsystem based only on local information that guarantees stability for the whole human prosthesis system. We consider systems with hybrid zero dynamics because in walking, there are impacts at foot strikes, meaning every time the foot hits the ground, there are discrete dynamics. Our hybrid system has these continuous dynamics and these discrete dynamics. There are domains of continuous dynamics and guards that trigger discrete dynamics based on a condition called H. In the case of a walking robot, H is when the foot hits the ground. When this goes to zero, the guard triggers the impact dynamics, which then can come back to the continuous dynamics. To consider the zero dynamics, these are the uncontrollable dynamics. And the hybrid zero dynamics, we require these to be stable on their own. The zero dynamics are when all the outputs, X, are zero. The system is reduced to a lower dimensional manifold and evolves on this space. We require that the evolution on this manifold be stable. And so we consider this our hybrid periodic orbit in the zero dynamics is stable when all the outputs are zero. However, if the outputs are not perfectly zero, what guarantees do we have of the stability of those zero dynamics? We must construct U such that we guarantee that those zero dynamics are stable even when the controllable dynamics hit an impact. We use a special class of CLF controllers to do this. CLFs are used to create a class of stable controllers, which is by having a positive definite function V that has a negative derivative to guarantee stability of the system. However, we need faster exponential convergence in the controllable dynamics such that we do not destabilize the zero dynamics at impact, so that every time the dynamics have discrete dynamics at that impact, the controller is able to quickly converge back to the trajectory such that the zero dynamics will not be destabilized. So we add an additional term in the construction of the CLF to increase the exponential convergence rate. Here's our positive definite function with these positive constants. And we add in this epsilon term, which we can adjust between 0 and 1 to obtain a convergence rate fast enough such that the zero dynamics will not be destabilized at impact. While these methods work well for walking robots, we cannot apply them directly to the prosthesis because the human dynamics are unknown. We consider the human prosthesis system in the context of separable systems, where when a subset of control inputs, namely UR, do not affect part of the system, the dynamics of XS, we obtain this form of a separable system, where we can call the unaffected part of the system the separable subsystem, which we have as the prosthesis, and we call the rest of the system as the remaining system, which we have in our example as the human. Then with special measurable states and inputs, we can create an equivalent subsystem where these dynamics are equivalent to that of the subsystem, but they are based on states that we can locally measure. Here for the prosthesis, these measurable states are the base coordinates, which can be measured with an IMU, and the measurable inputs is the force, which can be measured with a force sensor. I'll now present the main idea of Theorem 1. Using two res CLFs, one for the remaining system, the human, and one for the subsystem, the prosthesis, we obtain the same formal guarantees of hybrid zero dynamic stability in the full order system. The basic idea of how this is proved is by creating a composite Lyapunov function of these two res CLFs and show that when these individual conditions are satisfied, the composite Lyapunov condition is satisfied, guaranteeing stability for the whole system. This result is significant because when the remaining system is stabilized by a res CLF, a subsystem controller using only local information can guarantee stability of the full order dynamics. This result is shown in the case of the prosthesis when we plot the zero dynamics. Starting from a perturbed initial condition, the zero dynamics converge to their hybrid periodic orbit when the res CLF controller is acting on the prosthesis. For this, we do assume that the human can stabilize itself, but we consider this a reasonable assumption because humans exhibit limit cycles in walking, and our class of res CLF controllers contain all control inputs that stabilize these type of hybrid periodic orbits. Also, we have our prosthesis trajectory match human data and construct it such that it is stable with human-like trajectories. So this is human motion capture data in blue or in black, and the blue is the generated trajectory that we get from an optimization that guarantees stability. To present the main idea of Theorem 2, I will give a brief overview of how we construct CLFs using a linearized output system. We linearize the outputs with the feedback like this, with the feedback linearizing controller. And then we can solve the continuous time algebraic Riccati equation to obtain P to construct our CLF. With these constructions, we obtain a block diagonal form, and this yields to essentially be a summation of sub-CLFs. The main idea of Theorem 2 is that due to this block diagonal structure of the CLF constructed with linearized outputs, that by satisfying the conditions for the sub-CLFs, the overall CLF is stable. The basic idea for the proof is that looking at these sub-CLFs, and if we consider the inequality constraints for the derivatives, when we sum these together, it is bounded by the overall inequality condition, such that when each individual condition is satisfied, the overall condition for the Lyapunov function is satisfied and the system is stable. This image portrays how when the bound in purple is met by the CLF derivative in green for each block diagonal CLF, that then the CLF for the full system also is below its bound, meaning the system is stable. This result is significant because it means we can construct our auxiliary control input for the individual sub-CLFs with only their respective output, but then obtain stability for the full order system. In the case of the prosthesis, the bound for the human, the CLF derivative for the human is given in blue. For the prosthesis, it's given in red, and the overall CLF derivative for the system is given in purple, and it is below its bound, which is given in gray. In conclusion, we developed a class of subsystem controllers using local information that guarantees stability of the hybrid zero dynamics in the full order dynamics. This yields a class of model-dependent prosthesis controllers that relies solely on local information, yielding stable human prosthesis walking. An example of a controller that is in this class is this QP that minimizes over the feedback linearizing terms and satisfies our res CLF condition. This is a controller acting in this simulation video, and the control input is smooth. After this work, we applied this res CLF subsystem controller on a prosthesis platform in the stance phase and achieved stable human prosthesis walking. So this is a model-dependent prosthesis controller accounting for the interaction force from the human. This work has been submitted to ICRA and is posted on arXiv that you can view in the meantime. Future research will work to implement a res CLF during the swing phase and also improve the performance through the specific controller construction. The advantage of this work is that we created a whole class of controllers, so we now have flexibility in the exact controller construction we want to use that will still always give stability of the full system. Thank you for your attention, and with that, I would like to acknowledge my advisor, Dr. Erin Ames. I'm funded by the National Science Foundation, and here's my contact information. If you have any questions, I'd love to hear from you. Thank you.